morning, Bears. It's Thermal Energy Week 2, Day 4, Thursday, epic. Friday, epic. We wrap up our conclusions and we make a final, I think it is basically our final prediction back to our school plan. Which heating system are we going to use? We still have a little more information to get when we come back to science. And I'm contemplating keeping this unit going a few more days into next week because I do like to tie in our Roman Empire, ancient Christianity history week into Easter. So that would be best if we did that the week leading up to Easter break. So thinking out loud right now, but stay tuned. We might stay in a science week format halfway through next week. And that way we can then switch to ancient Rome and the spread of Christianity the last couple of days of next week, because I believe right before Easter break, no school on Friday. We start getting a little antsy because it is getting ready for spring break. So Thursday sometimes is nice to have a little bit of a Thursday fun day. That would only leave 3 days of that week. So as I plan it out, I think we're going to do it. So guess what? Let's stay focused in science through next Wednesday. We'll make it a Thursday, Friday epic. And then next week, we're going to really solve the problem of that school because those kids are cold. Well, how are you going to solve that problem? Who's going to solve that problem? People like Sophia, who have been doing the research, doing the Mandy's, checking her groups, and getting things done. Look at this top slide. Thermal energy. Week 2, hot, cold. Notice the heat's going that way. The cold's trying to go that way. But look at this yellow line. The heat flows this way. So what's going to happen? Is this going to cool off? Yes. Is this going to warm up? Yes. But keep in mind that cold doesn't necessarily cool off the heat. It does, temperature-wise. But as far as thermal energy, remember the heat is moving into the cold. And then so the heat is actually losing its thermal energy, which is increasing the thermal energy of the cold. And remember, the mass, as Lena pointed out yesterday, does factor in, and we're going to talk about that today. So if you want to have an A, your slideshow looks something like this. It doesn't even have to be this great. Look at this. Why does the transfer of energy stop between objects? She even has a video. This is fun to do this kind of thing. Look at this. Wow. Yeah. Oh, you want to see a grown man jump for joy and do flip-flops and cartwheels? Well, you're going to see one in a minute. This is advanced. Look at this. She's got her demonstration of her video of the sim, and it's showing what's happening, and she describes her energy transfer. I love it, Sophia. Thank you. You're going great places, Sophia. Now, remember, do you have to have all this? No. You can just have something about the energy transfer based on the sim and an image that you played with, or the picture. But man, that's great, Sophia. I'm going to read that one on tomorrow, student-led. I'm going to read that one. I'm going to read this one on student-led tomorrow because that's when we're learning the week from students' work. Another great, look at this, man. This is awesome. I can't wait to read this tomorrow, Sophia. Today we have to get our work done today. But, oh, look at this. Sophia, I didn't even know we had this graph option. Sophia's found something I didn't even know about. This is the first time I'm using these sims. Did not know that you could track and replay the sim. Oh, Sophia, love it. All right, we're gonna focus on this tomorrow so we can really learn. This is just an overview of what people need to have their work done. These could be images. She's gone next level. She has what will happen. She has more. Claim 2 is correct because as I observed in the sim and read in the article, energy can move from one thing to another or one place to another, but is never created or destroyed. So, okay, tomorrow, this is it for every class. I'm going through these 4, and you're going to learn everything you needed to know from Sophia tomorrow. If she wants to help me present, that would be fantastic. Right now, I just want to show you what slides you need to have. Equilibrium slide. What is thermal energy? Collisions. Transfer. Now remember, you folks at home still tracking heat transfer, thermal energy. They were just words. She made these slides come to life as a creative presentation with images. The words were already there. And so you can do this part. So even if you're not ready for these high level writing, you can find concepts and put pictures and get a C. If you're in class every day and participate and are a nice person, you might even be able to get a B because we're stressful environments. Love it, Sophia. So happy about all this. So happy. Thank you, Sophia. So there you go. Pause this video, go back to groups, and play 5 seconds at a time and go do work similar, not even as good as Sophia's, and you can just do the concepts and you can get a C. All right, now let's get on with today's. Well, before we get on today's lesson, I want to give everybody another. I do this all the time, and I feel bad for Sophia. She has to wait 3 minutes right now because, or she can go look at groups and start today's work if she'd like. But guess what? I just wanted to walk everybody through. And right now, if this is period 7, period 3, I'm gonna keep this video going. If it's not, I'm reminding myself stop video and do this with the other classes because I want to do this individual. So this period 3, this is what we're gonna do. I want to show you something. This is Star, beautiful characters of Greece. Guess what, Star? You have not submitted it. And I want to show you, I can't grade it if it's not submitted. There's no place for me to put the grade. So Star, go back to history. And Star might say, well, how do I do that? I can't remember. I'm going to show you. This is Chris's. Chris, guess what? You also have not submitted a slideshow that you've done work on. So watch this. You just go into your class, history. You scroll to the bottom. Now, all of these you should click and submit. But right now, for this week's grade, because I just noticed this, so I'm going to actually check the history grades again at the end of today, or by tomorrow for sure, because I don't have to do report cards till Tuesday. Come down here, Chris, and you click Characters of Greece. Now, this takes me to my version, so it doesn't look right. But watch this. You're still in submissions over here, Chris. You're still in submissions. I just saw it. Here you go. Chris D, check it out. You're still in submissions, yet you've got work done, buddy. You've got all the work done. I'm pretty sure I just lowered your grade, Chris. Go into history. Scroll to the bottom. Click Characters of Ancient Greece. Open it, and then there's a button called Submit. Star, you do it. Chris, you do it. And anybody else in this class, and I'll go pick a couple people from the other classes as well. All right, now let's go get on with our assignment. We're going to go ahead and keep using Sophia's slideshow. All right, so we still have to make our recommendation to Mr. Chang. Though you've only modeled one system, you need to give equal consideration to both and use what you have learned so far to help you decide which system you think is the better choice for the school at this time. Remember, we have school with hot water, 39 degrees, small tank. Morning temperature at the school, 11 degrees. Morning temperature at the school, 11 degrees. That doesn't change. Groundwater, this is existing groundwater, and it pumps in at 30 C. So we have way warmer water than the colder water. So, at first glance, we might say the smaller mass of water would heat this better than us colder, large mass. Is that right? Let's find out. It's okay if you're still not sure which heating system is better. You might change your mind as you learn more throughout the unit before you make your final recommendation. Which of the two systems do you think will do a better job warming Riverdale School and why? So everybody right now, what's your guess? You don't have to write it down, just in your mind. Let's do a Release the Kraken. Just put small tank, big tank. Small mass, big mass. Or you can say proposal 1, proposal 2. Write it in the chat. Do not release the Kraken. Write it in the chat because everybody will just copy you. Right now, you got about 30 seconds. Write it in the chat. Think about it. Look at the picture. Right. Release the Kraken. All right. If you're in Zoom, we'll see what people have. You can't be right or wrong yet, so it's okay. Now, the water inside the teacup is very hot, about 80 C. The water inside the bathtub is warm, about 40 C. So now we have a hot water and warm water. Which do you think has the greater average kinetic energy? The molecules of the water in the teacup or the tub? Some of you might already know this because of your experiments. Which do you think has the greater total kinetic energy? The molecules of the water in the teacup or in the tub? So we have two things here, average kinetic energy and total kinetic energy. So there's average, total, that's important. The comparison between the teacup and the bathtub is similar to the comparisons that you'll need to make between the two heating systems for Riverdale School. One system's reservoir is smaller but hotter, while the other system's reservoir is larger but not as hot. In this chapter, you will learn more about the difference between average and total kinetic energy to help you figure out which heating system will warm the air in the school more. Chapter 3 question, which heating system will warm the air in the school more? So here we go. Let's figure this thing out. That's our final question. Probably going to be our Thursday, Friday epic with examples and explanations. We need to find out which system will transfer more kinetic energy, since the school's temperature will increase more if more kinetic energy transfers to the air molecules. What determines how much total kinetic energy something has? So how do we know the total kinetic energy? Like I said, we've had some clues. We're going to read this little article to help us. You guys have probably getting along with the clues here that we like to read articles, we like to find evidence, we annotate, we highlight, we'll do that together, and then we use that evidence along with our experiments that we've done with the sim to come up with a conclusion. So let's get to the article. The article is in groups, but right now you can just follow along with the video. If the video doesn't work, if we're lagging, you can go open it and click the read along, and you can always read this on your own if you miss Zoom. All right, here we go. The article, remember, the article does not read these things. If you're a fast reader, you can read them or come back and read them later. Another thing is, don't forget, when you open this with your own ID, this is your document. This is like a piece of paper. It saves it for you. So as you're going, if something jumps out at you like, oh, small mug when you go to taste soup, that means nothing, obviously. You can take a note, you can highlight, then you can come take a note later. During a read aloud, you probably just want to highlight. Don't worry about notes. And then later you can come back and you're ready to give your reasoning or your explanation. If it's an ACE essay, if it's a CER essay, it's a reasoning. We have evidence, and then we write our reasoning, and then we're ready to write an essay. So remember, you can do that. You want to we do already know what we're looking for, right? We're looking for things about total average. We're looking for average kinetic energy, total kinetic energy, the difference between temperature and thermal energy. So thermal energy is not temperature. That means we probably want to know the difference. So if you get evidence about those differences that will help you in your CER about which air conditioner the school should use, and we're probably going to write that as a letter to the parents, explaining to them why we need to use a certain thing. So take little highlights along the way, and it just saves you some work later. All right, let's do this.
Thermal energy is not temperature. Imagine that you and your little brother are sitting in the kitchen on a cool autumn day. There's a pot of soup on the stove and both of you are hungry. You pour yourself a big bowl of soup, but your little brother can't eat that much, so you pour some into a small mug for him. When you go to taste the soup, however, you realize that it is still too hot. You could wait for the soup to cool by itself, but you're hungry now. So you grab 2 identical ice cubes from the freezer. You drop one into the bowl of soup and one into the mug of soup. Once both ice cubes have melted, you take a spoonful of soup from the bowl. The temperature is perfect, warm and hearty, but not too hot. You infer that your brother's soup is the same temperature. Have some, you say. Your brother dips his spoon into the mug, takes a sip, and makes a face. Mine's cold, he says. At first you think he's just complaining, but then you take a sip from his mug. It really is cold. What happened? Both the bowl of soup and the mug of soup started off at the same temperature, and you added identical ice cubes to each. So why did his mug get cold while your bowl stayed warm? Since the 2 containers of soup began at the same temperature, the molecules in the bowl of soup and the mug of soup started off with the same average kinetic energy. However, that doesn't mean they had the same thermal energy. Thermal energy is the total kinetic energy of the molecules of an object or material, and not the average kinetic energy. Each molecule in an object or sample adds its kinetic energy to the total kinetic energy. The bowl contains a lot more soup than the mug, and because soup is made of molecules, more soup means more molecules. Each additional molecule contributes the kinetic energy of its movement to the total kinetic energy. As a result, your bowl of soup has much higher total kinetic energy, thermal energy, than your brother's mug. Why is this important? Well, since the two ice cubes are identical, we know that the bowl of soup and the mug of soup each have to transfer the same amount of kinetic energy to the ice to melt it. In both cases, transferring that energy to the ice makes the soup cool down. However, in the case of the mug, this transfer of energy cools the soup much more because the mug doesn't have a very high total kinetic energy to begin with. The bowl has a much higher total kinetic energy because it contains a lot more molecules, each of which adds some energy to the total. Thanks to these extra molecules, the same transfer of kinetic energy has a smaller effect on the temperature of your bowl of soup than it does on your brother's mug. Let's say that you put your brother's mug of soup in the microwave to heat it up again. Now it's very hot, much hotter than your bowl of soup. The average kinetic energy of the molecules in your brother's cup of soup is higher than the average kinetic energy of the molecules in your bowl of soup. What about the total kinetic energy, thermal energy? Is it possible that your bowl of soup could have a lower average kinetic energy, temperature, but a higher total kinetic energy, thermal energy? Yes, your bowl of soup probably has a higher total kinetic energy than your brother's mug of soup because it contains more molecules. All of those molecules contribute to its total kinetic energy. To calculate the total kinetic energy of something, add up the kinetic energy of all its molecules. So even when something has a low average kinetic energy, temperature, and isn't very warm, it can have a high total kinetic energy, thermal energy, if it has a lot more molecules. Now imagine...
I think that's a good one for us to possibly highlight. Going to help you out here. So let's do this. Now remember, if you're following with this video, you have to remember where it is. Some of you guys have probably went and opened this. You have it in its own window. You're reading along with your own stuff. That's fine. But we can go back because we're going to come back and look at this again. So that's a good little highlight. Let's try some more.
Imagine that you're waiting for your soup to cool down and you leave it on the counter while you go do your homework. Your homework is so interesting that you forget all about your soup and now it's cold. Actually, if you were to measure the temperature, you'd find that your soup is the same temperature as the air in the room. What's going on? If you think of your bowl of soup and the air in the room as two parts of a system, then the explanation goes like this. Your soup is hotter and the air is cooler. Since energy always transfers from warmer things to cooler things, the kinetic energy of the molecules in your soup is transferred to the molecules in the air as the molecules collide with each other. The system continues to change, transferring kinetic energy between the soup and the air, until the soup and the air reach the same temperature. That is, their molecules have the same average kinetic energy. The soup and the air are in a stable state of equilibrium. Your soup seems to have cooled down quite a bit, but you probably don't notice any change in the temperature of the air. This is because there are many, many more air molecules than soup molecules, so the air has a much higher total kinetic energy, thermal energy, than the soup. And you would need to transfer a lot more energy in order to change the air's average kinetic energy, temperature. Remember, thermal energy and temperature are not the same thing.
So that's something. Notice this as we talk about CERs in your own writing. What is this? A conclusion sentence. What's our title sentence? Thermal energy is not temperature. So then they tell a story, but basically, introduction, claim, restate their claim. So just a little tie-in to our writing. All right, let's go back now and take a look at our Thursday, Friday epic. I've already basically told you what it is. We're going to, hold on, the problem of which heating system will warm the air in the school more. So this is our Thursday, Friday epic. I want you to write this as a letter to the principal. Or no, let's make it a letter to the parents. You could make it a letter to the principal. I think it's better a letter to the parents. As students, the parents are confused. Remember that one parent sitting there goes, how's that going to work? There's not enough water there to heat the school. We got to use the warmer one. So why would, when we go back to our school, this groundwater or this one be better? So let's talk about that real quick in the chat room, or the breakout rooms. We're going to go in the breakout rooms. You have the article. You can open the article. You have your sim experiences. Some of you have more than others. You have things that I have said. You have Lena's feedback, if you're in that class, that we need to find out which system will transfer more kinetic energy, total kinetic energy, since the school's temperature will increase more if more kinetic energy transfers to the air molecules. So knowing what we know, this picture, at some point, one of the slides with this picture needs to go to the top. We need to know this, what determines how much total kinetic energy. We're going to find that out right now. And then we're going to decide which heating system. And the today, Thursday, Friday epic is to use our information. Now remember, we talked about this earlier. How do you find the total? The average kinetic energy is when you add up numbers and then you divide the number. So, for example, add all the numbers to find a total, and then you divide that total by 3. 12 divided by 3 is 4. So the average is 4. What's the total kinetic energy, though? It's 12. 5, 6, 7, 8, 9. Remember, I did this scenario where if you have, I used 5, 6, and 7, but let's make it really easy. I have 1, 2, and 3. 1 plus 2 is 3. 3 plus 3 is 6. 6 divided by 3 is 2. 1, 2, 3. It's easy to figure out. The average is 2. You can add them up and divide by 3, and you're going to get 2. Well, what if you have 1,000, 2,000, 3,000? The average is, not 1,000, 2,000, 3,000. You have 1,000 ones. It's different than saying 1,000. 1,000 twos and 1,000 threes. And you have to get the average of all those numbers. Well, if you do that, you are going to end up with the average of still 2. That's it. Because you added them all up, you divided by the 3,000. So that's why total number, adding things together, is going to be different than average number. Temperature is average. That's why it equalizes on our sim. Total kinetic energy is not average. So if you have something, and let's just wrap it up with Lena. If you're not in her class, you don't remember this, but Lena very smartly mentioned that the mass of something, and that's why when we did the sim, and you can go play with the sim now to prove your theory and test it if you want, the mass of something impacts the total kinetic energy. So those of the people that played with it right yesterday are getting what I'm saying, because they put a big object and a small object. They heated up the small object, and they made the other object cold. And when they did the combo, they saw the energy shift, and we can see this, as a matter of fact, probably in Sophia's slideshows, that when they went together, let me see if I can find one of hers, just for fun, one we didn't see. And we'll watch this as I'm talking. Notice those are the same shape, so they will equalize. But imagine if one was larger, listen to my words, corroborate me with the text, with what you've learned with the sim, use whatever information you need to write your letter. The larger object will have more total kinetic energy. All right, that's all I can tell you. Now, what are you going to do? Final assignment. Create a top slide. I'm going to put all this in groups. And I'm going to move this down here so I can type. Letter to parents on your recommendation for which system. Now, you have notes, you have your article and everything else, but with the one thing you definitely have to have, you have your slides. You can refer to anything you want. Sophia could refer to any one of her slides. But the one thing you definitely want to move to the top is any one of the slides, doesn't matter which one. There's the one that some look like this, some look like this. I think I would move this one up because it doesn't have any words. Moving it up on the side, you can't see it. And now you can combine this with your letter, and maybe you even want to take only one of these. See, they're separate. The one you pick, you might want to put into your letter, almost like a brochure on why this proposal is the best proposal. Thursday, Friday, epic. Now that's A level. I just described A level. Sophia's tracking, Emma's tracking, Lena's tracking. People that get A's, you guys are tracking with what I'm saying. It's almost like this is too easy. I already know the answer, and I like writing letters. And they're going to write a letter, and they're going to talk about which one of these is best. If you're not tracking, guess what? Go find your concepts. Make these look cool. If I open a slideshow and just see these concepts, guess what? You're going to get a C, and you're going to get a C in class. If I open a slideshow and see this letter, you don't even have to do these because this letter is A level. That's high level thinking. You just do this letter, you're going to get an A or a B. So if you get it, write the letter. Do the letter. Explain which one of these is the best. All right. Epic day, because it's a Thursday, Friday. Epic. Tomorrow, student-led. We're going to go through Sophia's slideshow because she's going to teach us amazing stuff with there. And I'm going to let you have half a class to get work done. So you will have time tomorrow. But don't wait. Thursday, Friday, epic.